Hi, Chem 201 Organickers. One of the skills that you're going to have to become proficient in order to succeed in this class is remembering how to do electron configurations. That was part of your prerequisite requirement, but I always try to go over this a little bit in order to bring everybody up to speed and get them on the same page. So we're going to do a very quick session on how to develop electron configurations and how we're going to use them in organic chemistry, particularly with the elements that are most commonly found in organics, such as carbon, oxygen, nitrogen, sulfur, and phosphorus, those sorts of non-metallic atoms that you're going to see commonly in organic chemistry compounds. So I'm going to share my screen for a little bit in order to go over a few slides about electron configurations. So this is the review that we're actually going to be discussing at the moment. So in terms of electron configurations, recall that according to quantum mechanical theory, the electrons are going to populate orbitals around the nucleus of the atom in a very specific way. The electrons in atoms are going to exist in orbitals, and we can describe the occupation of those orbitals by electrons by writing an electron configuration for any particular atom. So we know the atomic number is generally equal to the number of electrons in that neutral atom. So if we look at hydrogen, which is atomic number 1, I have 1 electron that needs to be put around the atom into an orbital. I am filling my first energy shell, which is going to be this 1s this 1s orbital, right? That's going to be my electron configuration. This is the orbital type, which is an s. And then here's the number of the electrons that I have to put into those orbitals. So for hydrogen, my electron configuration is 1s1. Remember, we can also represent these electrons in actual orbitals where we project those orbitals as squares. So this would be the orbital box diagram of hydrogen. This square is going to represent the orbital. There's only 1 square, so it's going to be an s orbital. Remember, if I have p subshells, I have 3 different orbitals. If I have a d subshell, I have 5 different orbitals. And if I have an f subshell, I would have 7 different boxes, which represents the 7 different equal energy or degenerate orbitals. So in this case for hydrogen, this is our simplest element. So remember, I only have 1 electron. It is in the first energy shell in that lowest energy subshell, which is s. And I have 1 electron that populates this orbital. So I have a one-sided arrow. In this case, it's pointing up. The up or down direction is going to represent the spin of the electron. Conventionally, the first electron inside an orbital is usually conventionally indicated as a spin up. And then if I were to pair an electron in that same orbital, that would be with the single-headed arrow pointing down, which would be the spin down. Remember, the electron configuration is the description of which orbitals are occupied by electrons. Every single element on the periodic table is going to have a slightly different electron configuration because as I add protons to the nucleus, which changes the configuration or changes the identity of the element, I'm also adding electrons if I'm talking about my neutral atom. So remember, the number of protons is equal to the atomic number, and in the neutral atom, something that isn't ionized, the number of electrons is also equal to the atomic number, because to get a neutral atom, I have to have the same number of positive charges as I do negative charges, since protons are positive and electrons are negatively charged. To have a neutral atom, I have to have the same number of protons as electrons. Degenerate orbitals are those that have the same energy. So anything in the same subshell, for example, the 3p orbitals in that given subshell would have equal energy. Remember, if I use my box diagrams, I'm going to use this sort of representation for, let's say, the 2p subshell. And then I can populate with electrons as I fill up that subshell. My ground state electron configuration is going to be the lowest energy. That's typically what, if I just take the regular atomic number and populate all the orbitals in order of lowest energy to highest energy, I end up with the ground state electron configuration. I can promote electrons into higher energy orbitals by adding energy, but typically we're not going to worry about that right now. And then the Aufbau principle is this building up principle, and this is a guide for determining the filling order of the various orbitals that are available in a particular atom. There are a couple of terms we need to know, including that Aufbau principle. Another one is a Pauli exclusion principle. No two electrons in an atom may have the same set of 4 quantum numbers. Basically, what that means is I can only have 2 electrons ever in an individual orbital. So if I do pair 2 electrons into an orbital, I have to actually give them opposite spins. So when I do have an electron box diagram, if my first electron is spin up, my second electron is spin down, and basically I can have no more than 2 electrons in any given orbital. That's how I can populate my subshells. I know I have in every energy shell, I have 1 s orbital. I can only put 2 electrons in it. Therefore, I can only have 2 electrons per s subshell. When I go to the p subshell, I have 3 orbitals. 3 times 2 gives me 6 electrons. So I can have 6 electrons that populate a particular p subshell in a given energy level. This should be review, hopefully. If not, you're going to have to go back and look at some of the materials from your prereq class in order to sort of catch up a little bit. But knowing the number of orbitals in a sublevel allows us to determine the maximum number of electrons in any given sublevel. Again, the s sublevel has 1 orbital, so it can hold a maximum of 2 electrons. The p sublevel has 3 orbitals. It can hold 3 times 2, or a maximum of 6 electrons. D has 5 orbitals, so I can hold 10 electrons, and the F sublevel has 7 orbitals, and thus can hold 14 electrons. So anytime I'm filling a particular subshell, I'm going to fill that before I move on to the next one. So my S sublevel will have 1 orbital in every energy level. 2 electrons go into that. If I have an energy level that has p orbitals, that starts at the second energy level, right? I would fill the 2ps, and then I go to the 2, or I would fill the 2s with 2 electrons, and then I would go over and get the 2p. There's 3 orbitals, so I can put 6 electrons in that subshell. So let's do a couple of examples in order to illustrate this. Helium has 2 electrons, atomic number 2. It's the noble gas in the first row of the periodic table. Both electrons are in the first energy level, and both of those electrons are going to populate an s orbital. So my configuration is 1s2, right? The 1 is the energy level. The 2 is the type of orbital, and this is the number of electrons in that orbital. And then this is the orbital diagram. Remember, this is spin paired, since I have one electron pointing up and one electron pointing down. This is a general ordering for the populating these various atomic orbitals. I always start with 1s, and then I go up to 2s, then I go to the 2p, then the 3s, then the 3p. Now this is a little bit of an anomaly. The 4s is going to fill before the 3d. And then I sort of have that trend all the time. My s orbitals in any given energy level are going to fill before the d orbitals of the energy level prior to the s orbital that's filling. This will make a lot more sense when we correlate this to the periodic table, but this is just a diagram that sort of gives you this proposed filling order that indicates that those s orbitals are a little bit lower in energy than the d orbitals from the energy level prior to that s orbital. And that has a lot to do, if you've taken Chem 121, which is Gen Chem 1, you know why that happened. It has to do with penetration and shielding. If you haven't taken Chem 1 and you've taken one of the other chemistries like 101 or 110, then you're gonna not have actually discussed that too much. But the important part, regardless of what class you took to fulfill your prerequisite, is that this is the basic filling order for the various energy levels and subshells within each energy level. So here's some rules about filling the orbitals with electrons. According to the Aufbau principle, lower energy orbitals are going to fill before the higher energy orbitals. Any orbital can hold only 2 electrons, and they have to have opposite spins, right? So it has to be spin up and spin down if I pair them together. This again is called spin pairing. If 2 or more degenerate orbitals are available, I have to follow Hund's rule. So what that states is, if 2 or more orbitals with the same energy are available, 1 electron goes into each until all of those orbitals are half full, and then they start filling and pairing. So for example, if I have a p subshell and I have those 3 orbitals, I fill one with 1 spin up, I go to the second orbital, fill it with 1 spin up, then I have the third orbital and I fill that with a spin up. So all 3 of these electrons are in the same spin direction. They populate each individual p orbital until they are all half full, and then they start pairing. So the 4th electron in my p subshell is going to go into that first p orbital, and it's going to pair. So that 4th electron is going to spin down. The 5th is spin down, and then the 6th is spin down. What I end up with is all 3 of those p subshell orbitals filled with 2 electrons that are spin paired. So if I have a D or an F, I do the same thing. For D, I have up, 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 up. 5 of those D orbitals are going to be half filled before they start filling and spin pairing together. So that's Hund's rule. Here, I just want to reiterate to you, if you took 121, this is going to be the filling orders for any multiple electron atoms, and that's where I get the lowering of the S subshells relative to the D. So that is, there's a lot of different reasons for this. In a hydrogen atom, I don't actually see this, but I only have 1 electron. So we really don't have to focus on this. Just know that in all atoms, except for hydrogen, there is going to be some crossover of energies between one shell and another. So for example, in any electron that has multiple electrons, a 3d orbital is going to have a higher energy than a 4s, which means the 4s is going to fill first. So let's go through this sort of together. Hydrogen is atomic number 1 electron. It's in the first energy level, which is n equals 1. It's in the s orbital because that's the only orbital subshell that's available in the first energy level. So my electron configuration is 1s1. As I go across the periodic table, I'm going to look at helium. Again, atomic number 2, I have 2 electrons. So this is going to be 1s2. I'm filling my s orbital. I'm still in energy level 1 because I'm in the first row. So that is my n equals 1. I have 1s2. At this point, my first energy level is full because in the first energy level, I only have that s subshell available. So if I look on a periodic table, what I'm going to drop down now is to row 2, which is where I start off with lithium. Lithium is atomic number 3. This is where I start. It has 3 electrons. The first 2 electrons go in the 1s2, right? The first energy shell is filled. 2 of those 3 electrons fill up the 1s2 subshell in that first energy level. And then I'm in my second row. So I'm in energy level 2, which is n equals 2. I have 1 electron left to fill. So I put that in the lowest energy orbital in my second, or energy subshell in my second row, which happens to be S. Remember, S is filled before P, which is filled before D, which is filled before F. Thankfully, in this basic organic chemistry class, we really don't use a lot of the transition metals, and we don't really use a lot of the lactanides and actinides, so we really have to just focus on our s and our p orbitals for the most part. So these are going to be the most important orbitals for organic chemistry. But I do want to reiterate that we should at least be comfortable with knowing how these electrons populate all of the atoms on the periodic table. So here, if I go across a couple more elements, I'm going to get to nitrogen. Nitrogen has an atomic number of 7, right? I have 7 electrons that I need to populate. I'm going to fill up row 1. Nitrogen is in row 2, so I know that I'm in my second subshell still, or second energy level. So I fill 1s2, I have 2s2, and then I look at the 3 electrons that are left, and they're going to go in the p subshell. So what I just did there was I put 7 electrons total, and then they're distributed according to how they populate those subshells in any given energy level. So if I start looking at the orbital filling diagrams and I correlate that with electron configurations, for hydrogen, I have 1 electron, so I have a 1s1, right? If I look at helium, which is 1s2, what I have to think about, right, is that I'm going to put that second electron in there and I'm going to spin pair it. So that's what I see on this diagram here. If I look at lithium, I have the 1s orbital and I have the 2s orbital. So when I look at that orbital filling diagram, I have the first subshell filled, and then I have the 2s subshell filling. And then if I look at nitrogen, because I'm entering this p area, this is how I'm going to fill the actual orbitals. Remember, this is according to Hund's rule, where each one of those 3 p electrons is going to go into a p orbital separately before they start spin pairing. There's also a shorthand configuration for these electron configurations. If you get tired, especially when you get to an element like lead, which is atomic number 82, a lot of times you're sort of going, okay, it's 1s2, 2s2, 2b6, so on, so on, so on, and you always have to write all these different things. So we have an actual remedy for that. We're going to use the shorthand configuration for any element that's probably higher than row 2 or 3. And what we're going to do is we're going to take the noble gas of the row before it, and that's going to end up being this shorthand configuration. So neon has this configuration, 1s2, 2s2, 2p6, because it's atomic number 10. And that row 2 is now filled. So the second shell is now completely filled. So I can designate that as neon in brackets. So in order to make the sodium electron configuration and designate that in a shorthand configuration, I'm going to use the noble gas configuration in a bracket, and then this is going to be the row that's actually filling after I get past that noble gas that's indicated. So I have this shorthand configuration states I have the electron configuration of neon and I have 3s1. This is valid for any element. So if I look at phosphorus, which has the electron configuration 1s2, 2s2, 2p6, right? Again, this is the electron configuration of neon. This is the row that I'm filling. So when I look at the shorthand, I'm going to use the same thing. I have neon, which indicates all of these electrons, and then I have those valence electrons, right? Those electrons in my outermost shell that are responsible for bonding. That I have a 3s2, 3p3 in order to designate phosphorus in a shorthand configuration. And I can do this for any element on the periodic table. If I look at potassium, right, this entire scheme is actually argon. And then this is the row that's filling. And when I think about how to designate that, I can actually use this shorthand configuration. Instead of writing this whole sequence out, I can replace it with that shorthand configuration. So I'm not filling my paper with all these letters and numbers, but I know what's happening. As it turns out, the electrons in those valence, that valence shell, which in this case would be that 4s1 electron, controls the chemistry. Now, when I go back and I look at the periodic table, when I start filling the D shell, which is in those transition metals, right? I do have, for example, once I fill the 4s2, I do drop down and start filling 3D electrons. They are actually not considered to be valence, and there's good reasons for that, but this is just a summary, so I'm not going to go into that. So here again, if I have my scandium, which is in one of the transition metals that we're discussing, again, I have all of row 3 that is filled. Now I start filling the 4th row, but when I get to the D block, I have n-1. So in that 4th row, once I get to the D block, which is the transition metal block, so that's the piece in between those two sort of towers on the end, which are the S and the P block. Notice I go from 4s2, I drop down to 3, and I start filling those electrons. These are not considered valence because they're not in the outermost shell. The valence electrons for this particular atom would be those 4s2 electrons. So I've referenced valence electrons a couple of times, and I want you to recall that if I have the highest principal energy shell, those are going to be the valence electrons. These valence electrons are extremely important because those valence electrons actually determine how an atom behaves chemically and physically. Anything in a lower filled shell or filling shell in the D and the F case are considered core electrons, and those are not as involved chemically. Now, transition elements have their own type of chemistry, and it's robust, but for this course, we're really focusing on the S and the P subshells. In any given atom, we're looking at the nonmetals that are in the right of the periodic table. So even though they're very interesting, we don't really focus on them. Again, I just want you to review how these filling orders actually occur. So here's a review of these valence electrons. Recall that the group number from the periodic table, if you look at the A electrons, the group number is equal to the number of valence shell electrons that you have. Again, this is the S and the P blocks for representative elements. They're also called main group elements, right? So that's the first 2 columns and the last 6 columns. And if I go across and I look at group 1A through group 8A, these are my noble gases. I can see that as I fill the S and the P subshells, the only thing that's differing is the N value. The N is equal to the row number or the principal energy level. And as I go across, I can see that I fill the S, and then I start on the P. As I go across, I get to the N, which is the noble gas configuration, and I end up with 8 total electrons. I fill that shell, which is the NS2 and P6, N being, it could be row 2, it could be row 3, or whatever. So lithium has 1s1, sodium is 3s1. They're both in row 1A or group 1A. So they have the same number of valence electron, which is going to be 1. Chlorine and bromine, these are halogens. We talk about those a lot in Chem 201. Those halogens are group number 7. They have 7 valence electrons. So they actually have a total of 2 electrons in the S subshell and 5 electrons in the P subshell. You can tell when I look at these, this periodic table, the group number is indicative of the number of valence electrons. The only thing that changes is sort of the principal energy level, but the number and type of valence electrons are the same as I go down the column in the periodic table. In particular, those A elements, group 1A through 8A, which are those representative elements or main group elements that are really important in organic chemistry. So the group number corresponds to the number of valence electrons. The length of each block is the maximum number of electrons the sublevel can hold. So the S block can hold 2 electrons, the P block can hold 6, the D block can hold 10 because it has 5 individual orbitals. The period number, which is the row number, is going to correspond to the principal energy level of those valence electrons. Again, we're usually focusing on the S and the P. Now, it's really easy to derive electron configurations using the periodic table if I look at where these electrons are located. 1s fills first, then 2s, then 2p. Once that's filled, I go down to 3s, then 3p. If you follow along this diagram on the periodic table, you're going to notice that this follows well with the rows and the columns in the periodic table. Once I get to 4s, when I fill those 2 electrons, the next thing is that transition metal block, and I start with n-1, which would be 4 minus 1, so that gives me the 3. Then I go back up to 4 to fill 4p. The same thing happens. I start with 5s. This is row 5, but my D, my transition metals, start with n-1, which would be a 4, and so on and so forth. It isn't until the 6th row that I start getting those inner transition metals into the mix. Again, we're not going to really focus on them in this basic organic chemistry class, so we'll leave those alone right now. So what you should be able to do is use the periodic table to assign the electron configuration for any of the elements in the first 4 or 5 rows. We're really not going to worry about those F elements, but we are going to worry about most of these other elements. Again, in organic chemistry, we're up in this range, which are my non-metallic elements that actually form covalent bonds. Carbon is my most famous organic chemistry element. We're going to focus a lot on carbon compounds in this class, but also recognize that nitrogen, oxygen, the halogens, sulfur, phosphorus, a lot of those other non-metallic elements are also important in organic chemistry. Here's another example of how I can use the periodic table in order to assign electron configurations. I really just start at the top and then I go across. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and then I keep going. When I get to the 4th row, this is 4s1, 4s2. This starts with 3d1, 3d2, all the way up to 3d10. Then I start back with the 4p's because I'm in row number 4. So this is my D block, and this is always n-1. So that's row number -1 when I start filling those. And again, we're really not going to worry about those F's for this class. So you can see that the valence shell, or the outer shell, is indicated in this particular example. And any column, right, the columns are going to have the same number and type of valence electrons. And then these, we're going to also look at the transition metals, which are the D electrons, but we're really not going to worry about those too much for this particular class. But even here, my columns are giving me an indication as I go down the column, except when I get into this area, which gets a lot more complicated. I generally have the same electron configuration as I go down the column in a periodic table. But again, we're really focusing on the S and on the P blocks over here in terms of organic chemistry. So those are the electron configurations that you should particularly be concerned with, especially above this line. We're really going to focus on elements that are in this area of the periodic table, also including the halogens. So iodine is a really important element in the periodic table as we go through this course. So another little topic I want to discuss for 2 seconds. Remember that I can form ionic compounds in regular general chemistry. And we see that many metals and nonmetals will form one ion. That ion is predictable based on the position, and it corresponds to the representative or the group, main group elements. And that's because I'm looking at the S and the P electrons only. When I look at transition metals, I'm going to have a much different consideration of atomic or ion charges, because they are multivalent and they form more than one type of ion. But when I look at the representative elements, which deal with the S and the P electrons, I can use the position of the periodic table to predict what the ion charge is. Group 1A always forms a 1+. Group 2A always forms a 2+. Group 7A will gain an electron to become like a noble gas. Group 6A will gain 2 electrons, become 2-. Remember, if I lose electrons, I'm losing negative charge, I become positive. If I gain electrons, I'm gaining negative charge, I become negative. So I'm always looking at how to become isoelectronic with the nearest noble gas. I want to be like the noble gas. So when I look on the periodic table, these are elements that'll form ions that have predictable charges. Group 1A always loses 1 electron, becomes +1. This will lose 2 electrons, become +2. Aluminum will lose 3 electrons, become +3. And then this will gain 3 electrons, become -3. This will gain 2 electrons, become -2. And this will gain 1 electron, become -1. So you can use the periodic table, especially those representative atoms, in order to figure out the electron configuration for these various ions. Recall that, for example, sodium is a group 1A metal. It's going to lose an electron. It becomes like the nearest noble gas. Chlorine is going to gain an electron to become like the nearest noble gas, right? I want to fill that magic number 8, the octet rule. I want to get the same electron configuration as a noble gas. Metals will lose to become positively charged cations. Nonmetals will gain to become negatively charged anions. The number of electrons any atom loses or gains is indicative of how it will become like the nearest noble gas, so the isoelectronic with that. So that's the whole game plan to become an ion. So if I look at anything in group 6A, I'm going to gain 2 electrons to fill that outer shell of S and P sublevels. If I have a 7A atom, I'm going to gain 1 electron to become like the noble gas there. It doesn't matter which 6A atom I am, because I can always gain 2 electrons to become like the noble gas next to it. Or I can lose 2 electrons in order to become like the noble gas before it. Or if I'm in 7A, okay, I just sort of screwed that up. Let's review this one. If I'm in 6A, I'm going to gain 2 electrons to become like the noble gas next to it and fill the outer shell. If I'm in group 7A, I'm going to gain 1 electron and become like the noble gas next to it, and that would become -1, right? So those 2 atoms are actually nonmetals. On the right hand of the periodic table, they're going to gain electrons to form negatively charged anion. If I'm a metal in group 1, 2, or 3A, I'm going to lose electrons to become a positively charged cation. So here's some examples of these sorts of trends. If I look across the periodic table, typically in group 1A, I form +1 cations. In group 2A, I form +2 cations. Group 3A, aluminum will form a +3. These will also do other things. In group 6A, oxygen and anything below it, I can form a 2- if they undergo ion formation. The halogens will form -1. What you notice here is group 4 is missing, and that includes carbon. Carbon actually likes to not gain or lose, but share in a covalent bond. And we're going to see that that is one of the reasons why carbon atoms are so ubiquitous in organic chemistry. So let's practice just for a second. I have these 3 electron configurations that I want you to write. I have carbon, I have selenium, and I have nitrogen. Again, I want to use the periodic table in order to do this. So what I'm going to do is I'm going to look where carbon is. It has atomic number 6. So I have to populate with 6 electrons. I start here. I go 1s1. Then I go 1s2. I'm filled. Then I drop to row 2. I have 2s1, 2s2. I'm filled. And then I have 2p1, 2p2, right? And that has a total of 6 electrons. So this is the electron configuration for carbon. If I look at selenium, selenium is down here, right? So this is in row 1, 2, 3, 4. So I could start at the beginning. This is atomic number 34. So I have 34 electrons, 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 3, 4, 5, 6. Drop down to the 3rd row, 3s2 is full. Come here, now I have 3p6 is full, drop down. I have 4s2. Now here, I have my row below, right? So this would be 3d10. And then I have 1, 2, 3, 4. I go back up to 4p4. I can use the noble gas for this, which is argon, and I can call it argon. And then I can do, starting at this row, I have to do all of this in my, after my noble gas. So notice that's going to be 4s2, 3d10, 4p4, and that would be the shorthand configuration. The other one that we wanted to look at was nitrogen, right? If I have nitrogen, I'm over here. That's right next to carbon. It's atomic number 7. So basically it's 1s2, 2s2, 2p3, right? Where I go here, I could also call this helium, 2s2, 2p3. So hopefully this gives you an overview of what you need to know for electron configurations. As always, if you have any questions, let me know and I will be happy to help you. All right, see you next time.